Hello everyone and welcome back to another video here in the Hidden Quantum Champions series on the Polaris School of Quantum. Today we are looking at a company called Quantum Diamonds. You know, diamonds are the girl's best friends and hopefully also your best friends, because that's what we're going to look into today. And with that, let's jump right into their website. So here we are at the Quantum Diamonds website. It says Quantum Diamonds Sensor Technology, and as you all know, we are looking at companies from the whole quantum stack. So that includes quantum computing, quantum communication, and quantum sensing. And today we are looking at a sensor company. So what do they actually build? It says making the invisible visible. In the background we see a wafer with some wafer structures on there and some light shining on it. It says 3D defect imaging, so extract electrical activity images from microelectronics for failure analysis, process optimization, and yield improvement. Then it says unmatched depth reach, see-through packages and stacks of devices to identify metal defects that are buried and unreachable optically. And then it says nanoscale resolution achieved down to 200 nanometers lateral and 1 micrometer depth resolution, pinpointing defect localization in 3D. So what does all of that mean? Let's go through it bit by bit. Let's take it apart bit by bit. So what we can already say, and I mean that's also something that is indicated here, is we are talking about an analytics instrument for semiconductor technology. That's why we see this wafer here in the background. So this time it's not a wafer of a quantum chip. Maybe it is, but this time we are not talking about any quantum chips here. This time we are talking about a sensor, and it says 3D defect imaging. So what do we mean by that? If you are looking at the transistors, so the chips that are into today's telephones, but also the AI chips, whatever, like what NVIDIA is building, what basically TSMC is manufacturing, what Intel is manufacturing, and what is extremely relevant is what they call the yield, and that's also why it says here yield improvement. So if you have a wafer like this one, you see there are these cells on here, so multiple different cells, and they are copies of each other. So usually you're not building just one chip at a time, so one processor for your computer at a time, but each single one of them is basically one processor. And now these processors, they're not built in just one step. There are many lithography steps, so many different fabrication steps that have to happen step by step. And they have to happen in this ultra clean environment. And I mean ultra clean means it's being purified air, purified chemicals, but still it can always happen that for some reason some dirt is introduced, there's some misalignment in a step or whatever, but usually it's like a dirt particle, and that's just a probabilistic process. So the bigger your chip surface area is, the higher is the probability that something might happen during the processing step. Like there might be one step where there's a particle falling on there. There might be a step where some chemical is off or whatever. And there are different strategies how to deal with that. In some cases, you just have to throw away the element. If it's like really in an unfortunate position, you cannot, let's say, just switch off part of it. You don't have any, let's say, way to mitigate this problem. And then you really have to throw away the chip. And that's the yield. And actually, if you look into semiconductor history, so semiconductor manufacturing history, there used to be many companies at the very beginning that were producing those chips. But at the end, if we look at today's landscape, we see that there's only a very tiny amount of companies that are still manufacturing semiconductors. And one of the main reasons for that was actually the yield. So how many chips do you have to produce to get one that is working, or the other way around, if you're producing 100, how many of these can you actually sell? Because if your yield is only, let's say 20%, and you're producing 80% for the dustbin, that's actually quite a problem, because then the chips become quite expensive, and that's why like there's economy of scale involved, right? And that's why it is important to, when you have some defect, when you have to throw away chips, you need to be able to analyze what is actually happening, where is this coming from, and how can this be mitigated. And I mean, there are different strategies of also how to deal with that. Think about these modern CPU architectures. I think there was some news also about that some of these companies that are making these multi-core processors, when you have, 4 cores on there or 8 cores and one of them is not working, you just turn off part of your transistor, or you just of your processor, or you just laser cut one part that it's not functioning anymore. And then you have, instead of an octa-core, you have a quad-core processor, and you just sell it as a quad-core. So there was some news about things like that happening, and that's essentially to turn what fell off because of your low yield into something else that you can still sell. So you reduce your loss basically on that. And this company here is making a sensor, as it seems, that helps to identify the issue that has been causing that. So that helps to extract electrical activity images from microelectronics. So then you can see where the currents are flowing, if there's a shortcut, where there's not supposed to be a shortcut, things like that, for failure analysis, process optimization, and yield improvement. So by that you can figure out, is there something wrong in my lithography step? Is there something wrong in the evaporation step where the metal was evaporated on the system? And that way you can improve the processes and thereby also optimize your process or improve your yield. Then it says unmatched depth reach. So see through packages and stacks of devices to identify metal defects that are buried and unreachable optically. That's kind of clear, right? If you're looking at it with a microscope, like here in this picture, you can of course only see the surface. Now, there are certain sheets that are transparent. If you think about, for example, transparent oxides, there are some oxides that you can actually see through, like for example, your glass window at home. But then, of course, there are also other ones which you might not be able to see through. So sometimes you can see more with an optical microscope, more than just the top layer. But oftentimes you really only just see the top layer of your structure. So if you have a stack of layers, and usually a transistor infrastructure, a chip is multiple of these layers, hundred of layers maybe even, then you cannot really see what is happening in the lower areas. And let's say there are certain microscopes that have a little bit more invasive or aggressive strategies, but usually you cannot see all the way down into it without cutting it. And here it says with this technology you can actually also depth measure the current profile, so where the currents are flowing, right? And then it's nanoscale resolution. So now we are looking at the lateral resolution, as in how precise you can kind of map something. You can scan something, and here it says 200 nanometers lateral and 1 micrometer depth resolution. So just as a quick reference, so 1 micrometer is actually quite deep already. If you think about oxides that are produced, for example, as barriers for the top gate on a transistor, you're usually talking about a couple of nanometers. So if you can scan micrometers down into the system, you can actually reach quite well all the way down. And that's, I think, also helpful, because sometimes you cap stuff on the top, you put some layers, protective layers on the top, and then it really helps that you have something where you can measure deeper down. And then 200 nanometers lateral resolution. I mean, looking at today's nodes, process nodes that are like in the single to 2-digit nanometers of device sizes. Of course, 200 might seem a lot, but I mean, then still, if you're looking in specific types of technologies, 200 nanometers is actually still where things are being processed. And also sometimes you don't need to know exactly the transistor, right? You just need to know which part of the chip is the error happening in, like which local area in the chip. And there you don't need to know the exact device, but maybe you want to find, within your processor in a specific area that is responsible for running the addition calculations. You want to know where in there this error is happening. And then I think 200 nanometer is quite helpful. So 3D. Okay, what else can we learn here? So the mission. Diamonds develops next-generation testing tools to push the boundaries of semiconductor failure analysis. And maybe also on that, I mean, it sounds like a very, let's say, top-level statement, but I think what is important to point out here, again, it's semiconductor failure analysis. So semiconductor is still the biggest market, right? So they are still selling millions of pieces every year. They are like super big fabs. The biggest tech companies like Nvidia, Intel, they are all more or less in the semiconductor space. TSMC, of course, as a manufacturer, Intel as a manufacturer, they are in this space. But also the companies like Qualcomm and Nvidia, they are interested, of course, in understanding where the errors are happening. They want to understand or improve the quality of the chips, and therefore for them it's also interesting to know those type of things and to have those insights here. So I think that's interesting to note also in this quantum revolution. Here we are talking about quantum sensors. They might on the first glimpse not be as exciting as quantum computers, but they actually already create value here, right? So they are serving the semiconductor industry with their tools at a precision that has never been there before because of the quantum technology that is within it. And I hope we will learn a little bit more about that when we go here to our technology. But they're already creating value today, and they are creating value for an industry that is making money already today. So that's very interesting, right? Okay, then we have the newsroom here. I'm recording that end of November, and we see also here the last news is from November 26. Quantum Diamonds wins German Physical Society Award for outstanding achievements in translating state-of-the-art physics into industrial applications. From that, I would assume that they are a German company because they won the German Physical Society Prize. Let's move down a little bit. Here it says our products and services take semiconductor testing into the next level. So now let's learn what they actually offer. Quantum Diamonds develops and deploys next generation testing tools for the advanced packaging area, offers in-house failure analysis with quantum sensing as a service, as well as provides world-class standalone quantum sensors. So they have the standalone quantum sensors, which we see here on the left side, which is the base component, right? It says calibration-free quantum sensors of the highest caliber based on synthetic diamonds. Then they have the tools which they are selling, right? So the next generation testing tools which have the sensors integrated in them. It says advanced semiconductor testing tools based on quantum sensing for defect localization, yield improvement, and process control. And then finally, they also have this in-house testing service. So that is a service, I assume, based on this machine. And it says failure analysis performed with our in-house testing systems and comprehensive reporting. So you can also send a chip there. So they cater 3 different categories. One is instrument makers that need to buy sensors for their specific type of instrument. Then they are an instrument maker themselves, so they create their own tools and sell them. And they're also a service provider, so if you have a chip, you can send it there. And here in this picture, we have an Apple one, so who knows, maybe Apple is also a customer of theirs. Unprecedented depth, reach, resolution, and speed for testing advanced semiconductors, our technology metrics. So magnetic current imaging, that's what we heard before, right? So they're doing this 3D imaging capability, imaging of metallization down to 200 nanometers feature size for advanced back end of line, for example, hybrid bonding, advanced package. Packaging is when the chip kind of gets into its housing, because usually you don't have, let's say, the silicon chip itself exposed to the PCB where it is mounted on, right? So there's a packaging around it, like some type of plastic molding maybe, but also there are other ways, ceramics and whatever. And then bonding is where the chip is actually, so the silicon chip itself is connected to some metal leads that somehow can be connected to the printed circuit board, to the PCB here, right? Because you have the chip that is somehow sitting on here, and it has to be soldered on top. And this connection between the silicon and the solder bonds here, more or less, is the bonding technique. So they are specializing in hybrid bonding and in advanced packaging analytics or imaging. Depth reach up to 500 micrometers. And I mean, if you have a plastic package, that's also kind of what you need, right? You will not talk about nanometer scale as in like how the transistor itself is like stacked up, but when you put the plastic on top, you're usually talking about micrometers, and the depth resolution up to 1 micrometer. And then wide field technique, so the wide field imaging, no raster scan required for areas of up to 4 by 4 millimeters field of view. Stitching of wide field images available for samples of centimeter size. So you can really, with one scan, so you don't have, let's say, a scanning probe that is going one by one and measuring in this 200 nanometer distance 1 point, but you really have, let's say, the full view, and the full view goes up to 4 by 4 millimeters. So you can see 4 to 4 millimeters at a resolution down to 200 nanometers of feature size. And then you can stitch multiple of those together so that they are like tiles in a bigger picture. And then you can go all the way up to centimeter size. So you can basically scan through this here in a 4 by 4 millimeter window, and then measure essentially the whole chip, which is centimeter size. So that way you could take a current image of the full chip, probably even while it's running, because, and that's I think the interesting part here, it has a room temperature operation. So you can probably even, you will probably even plug it in. You can also see it here, right? It is hooked on this so-called breadboard. So there are like electrical connections here. So you can see there are like these little resistors down here, and they are basically biasing this chip up here, and then you can basically run the chip at its normal operation and observe with this quantum sensor here more or less the current profile within this chip at a 200 nanometer resolution, down to 200 nanometer resolution. It says robust imaging and testing at room temperature, stable down to cryogenic temperatures, and up to 700 degrees Celsius, which is quite a lot. I mean, usually chips don't go up to 700, right? If you have a chip in your computer, it might go up to 100 within the chip. Especially if no cooling stuff is on top, it might even heat up a little more. But then 700 Celsius, I think, is already quite a lot. Our engagements in the quantum race, read about our partner projects. So there's the European Innovation Council is involved here, the Munich Quantum Valley. Then we see SPRIN-D project, designing a demonstrator that enables very high resolution while maintaining fast measurement speeds through sprung innovation. Then the European Space Agency Business Incubation Center is also involved from the ESA. And then we see the European Council again. The QD in numbers, so Quantum Diamonds in numbers, it was founded in 2022. So that is like probably end of pandemic time, right? Fundraised is 7 million euros and 35 employees, according to what they say here. Then, also very interesting, Quantum Diamonds strategically partners across industries, research, and academia to commercialize quantum sensing technology for semiconductor testing. And here I think it's getting very interesting. Of course, we see here what we've heard before, right? So we see the European Innovation Council. We also see the Munich Quantum Valley as a partner, and the Fraunhofer Institute in Germany, and the SPRIN-D, SPRIN-D. But then there are also some very interesting names popping up here. So when venture capital side, you see Early Bird, for example, which I think is internationally quite well known. But then also you see on the company side, there's Nvidia and there's Intel on here. So you see the big players that are actually involved in the production of semiconductors like Intel, but also are involved heavily in the chip design like Nvidia. They have an interest on that. So if we are looking here at the industry partners, we see also MEY as an industry partner. They have a very big interest in having those quantum-powered analytics tools. So, and yeah, then there's this, of course, as per usual, interested to learn more. And there are the typical things down here, like the About page and the social media. Let's quickly look at the technology side of things. So it says the first commercial provider of quantum sensing technology. So we see the 3D defect imaging, unmatched depth reach, and nanoscale resolution. I'm quickly reading what it says here. So we have created diamond-based quantum sensors at the atomic scale capable of operating in extreme conditions. Our quantum sensing technology utilizes solid-state qubits integrated into diamonds, probably, I guess, like NV sensors, which we've seen before also in other episodes. Quick note here, if you haven't seen all of the videos yet, go check out the Hidden Quantum Champions playlist on our YouTube channel. Moving on, quantum sensing transcends physical limitations in terms of spatial resolution and sensitivity, surpassing the capabilities of classical sensors. And then we see some pictures here from the people in the lab with their laser protection glasses on. So I guess lasers are somehow involved. Here's also some optical table with some lenses and other instruments. And here we see a probing station, I guess. So you have like this rotatable table. There's some probably even high frequency wire connection here. We see again the same as before, our current measurement limits. And then down here we see the partners again. Here it says we build next-gen testing tools based on quantum sensing that detect issues early, reduce waste, and improve yield. Our tools help fabs to detect defects early, preventing rework and scrap, reduce material loss through fewer lost wafers and excursions, and then have direct impact on scope 3, less CO2, fewer inputs, more output. And that's the idea of yield. And here we see such a chip, and that's what I was referring to before. So you see there are like different units on this chip, like here. So sometimes you have a storage, there's somewhere like an ASIC unit, there might be somewhere a process, like a RISC processor or something, or an ARM core, whatever on there. So you have these different units, and that's why you don't need to have a single nanometer type of precision. You just want to know, is it happening somewhere in here, or is it happening here, or here, or here? And that is a precision of, this is probably even millimeters, and then when you zoom in here, this is probably still in the micrometer range. So if you can go to nanometer, 200 nanometer, you can probably even say it's somewhere here, I would guess. Quickly also on our impact, what do we find here? We see a pick and place machine. So these are the machines that are placing the different semiconductor components on the printed circuit boards. So this is in the assembly of the full electronic component. Our impact, so the semiconductor industry faces a climate challenge. Semiconductor demand is rising, and so is the environmental footprint. At the current pace, semiconductor manufacturing is projected to emit 3.5 times more greenhouse gases than the amount allowed to keep global warming below 1.5 degrees Celsius, the global carbon budget set by climate targets. 3.5 times more emission projected, and then it says here carbon budget semiconductor industry 2050, actual carbon emissions of the semiconductor industry 2050. So you see there is much more. So 172 million MT CO2 emission. So from semiconductor fabrication in 2024, with projection to top 277 million tons of million tons of CO2 equivalent by 2030. 75% share of a phone footprint. Most of a phone's carbon footprint occurs during its fabrication, with about half of that coming from semiconductor manufacturing, and then 3% by 2040 share of world emissions projected contribution from integrated circuit manufacturing in trends continue. So there's a heavy focus on using that technology to become more green, to reduce CO2 emissions. And I mean, also if you think about yield, right, it also optimizes cost. It optimizes the chemicals that are being used, because if you have a low yield, still the market is requesting those chips, then you're just making more, which means you have to use more chemicals, more acids, more whatever, and you throw away more. So there's of course the CO2, but there's also other chemicals involved, other processes involved, of course more energy which is being consumed. So this has a huge impact, and that's just because semiconductors are such a scale product. So they have such a large scale. If you have something where you only make one item per year, okay, if your process is not super much more efficient, then it probably means that you have a little more emission. But semiconductors are large scale products, so there it makes a big difference, right? Then it says designing for what's next, advanced packaging, SiC, so silicon carbide power chips, so silicon and carbon power chips, so for power electronics, and 3D integration increases manufacturing complexity. Better testing during the production process boosts final yield and reduces CO2 per shipped chip. Every defective die is usually the little silicon part of the chip, consumes the same energy as a functional one. By detecting early stage defects, tightening process control, and minimizing scrap and rework, semiconductor testing directly improves both yield and emissions. Yet, as device architectures advance, traditional electrical and optical techniques struggle to probe deeply buried features and stacked interconnects. Quantum Diamonds delivers next-generation semiconductor testing tools based on diamond quantum sensing, closing critical monitoring gaps in these frontiers. With that, as always, we quickly go also on the About Us page to quickly learn about the team behind this new technology, behind this revolutionary technology. It says here, we help the world build better semiconductors. Semiconductor startup to watch, as highlighted by Sifted. Then first of its kind quantum sensing tool by with synthetic diamonds, and uncovers hidden defects in 3D semiconductors non-destructively and ultra fast. Who we are? We build next generation testing tools based on quantum sensing to solve one of the semiconductor industry's hardest problems. At Quantum Diamonds, we are building a new class of testing tools that use quantum sensors to see deeper, measure faster, and reveal what other tools can't. We aim to bring this capability into every advanced semiconductor fab and redefine what's possible in testing and yield optimization. And then here we see some pictures of this beautiful tool. I guess this is kind of the probe which you physically maybe put on the chip to with the little NV centers or the qubits in the synthetic diamond, and then you have some laser shining on it and evaluating, let's say, the qubit position, so the spin position, and by that you can see the magnetic changes, and by that you can measure the current, right? Because when you run a current through some wire, for example, it produces a magnetic field. So that's like a magnetic field wrapped around the wire. And for example, if you have then a current running like this, you will see that there is some magnetic field going in one direction and in the other direction, depending on the wire. And if you coil them up, you end up with an electromagnet, right? That's how these big electromagnets in the trash sorting, for example, work. And now if you have a very, very sensitive sensor, you can measure not only from a normal wire like this, but you can measure really from these nanostructures here, from these transistors, the currents that are actually running through by using the magnetic field that they are producing. And then, of course, I assume you can also measure that down into the depth of your chip, because the magnetic field is just going through those, right? Because unless you have a magnetic shielding in there, like a superconductor would be, you can actually just measure the magnetic field all the way down into the chip. And if your sensor is really, really sensitive, you can measure, and these are really, really sensitive, you can measure currents that are going like micrometers deep into the chip, even if they are very, very small currents. And I guess that's what's happening here. And then in this diamond, you probably have those qubits. You're shining some laser on it, and you are optically detecting the position of these. And if they are placed, let's say, at a 200 nanometer type of distance, you can probably probe those individually and thereby access the information at a 200 nanometer resolution. That would be my best guess. Our mission at Quantum Diamonds, we are redefining semiconductor testing. Our mission is to unleash the full potential of quantum sensing to deliver unprecedented precision in magnetic and electric field imaging. We aim to disrupt conventional semiconductor testing methods and accelerate fault localization deep within 3D semiconductor architectures. Here we see some green laser in the background. Our vision: we envision a future where we help the world build better semiconductors. Our technology will set the global benchmark for non-destructive, ultra-precise electrical and magnetical imaging. By enabling deep insight into complex 3D architectures, Quantum Diamonds will empower semiconductor manufacturing to accelerate design cycles, boost yield, and drive the next wave of high-performance, energy-efficient electronics while reducing waste and lowering the carbon footprint of semiconductor production. What we truly believe in: sense opportunities and focus on the customer. We see around the corner and seek out opportunities to adapt our product to suit evolving customer preferences and market dynamics. Better done than perfect. Perfection is the enemy of innovation. We are not in the business of the steady and stable. Just deliver, go the extra mile, and push the boundaries in every interaction, project, and endeavor. Be proactive. It's on you. Don't wait to be told what to do. It's your responsibility to see ahead and own solutions. And in knowledge flows, success grows. Communicate with your team and the golden triangle of business, hardware, and software. This is the only way to succeed as a whole. And then research to revenue. Here, I guess we see the two founders, the CEO and the CTO. So the CTO is Dr. Fleming Brookmeyer, and the CEO is Kevin Berghoff. I guess they are both here on the picture. It seems, or both on the image. They seem to have both worked on the TU Munich in Germany before. And then we see here for the CEO that he has been working in the consulting field, and I guess for the CTO in the research field, also at ETH Zurich, and then quantum sensing at TU Munich. We also see here the NV-based pulsed field gradient, NMR. So the NV is something that I mentioned before, which is probably the sensing technology. And here we see the whole team, a stellar team from multidisciplinary backgrounds. We are a group of physicists, engineers, and builders turning quantum science into production-ready hardware. Our team combines academic depth with startup execution, bringing experience from leading institutions and companies like TU Munich, ETH Zurich, LMU in Munich, Harvard, McKinsey, Intel, Airbus, and Infineon. And that's the whole team. And there's also some experts here, I guess, in some type of advisory board. Yeah, our advisors are industry-leading experts guiding us with their multi-year experience. So here we see people from different areas, I guess. We have professor from a university, Professor Dr. Dominik Bucher. We have people from the industry, TSMC as well. Foundry technology enablement at Intel. So I guess all the big names, ASML as one of the biggest silicon industry tool makers in the world. and of course in Europe. So you see all the big names are here also in the advisory board. And then there's a little bit of a time graph here with the funding in 2022, 2023, the 7 million seed funding round, launch diamond microscope paper in ASM International, official product launch in 2024. And then again, we see here the partners. With that, I think we are already at the end of today's episode. If you liked it, then please make sure to subscribe to the channel to not miss out on the next video, and also share it with a friend. Always happy to see new people here on the channel. And with that, see you in the next video. As always, make sure to stay hydrated. Until then, bye bye.